Yeah, welcome everybody. I'd love to introduce Kate Maher from Stanford, who's been working on carbon removal technologies and how they fit into, well, the wider palette of options we have for dealing with climate change, focusing on, I think, like enhanced rock weathering and that family of technologies. Yeah, welcome, Kate.
Great. Well, thanks, Greg. Thanks, everyone. I'm excited to talk to you all today. As just a little bit of background, I spent a lot of my career focused on studying two related topics. One was the contamination of soils and groundwater that was coming from both human released as well as what we call geogenic contaminants. So these are things that are released from the rocks themselves. So uranium and chromium are two examples, especially in California. There's been a lot of concern about chromium. And of course, in those contexts, we want to understand how fast and what are the rates of mineral dissolution reactions and precipitation reactions that control those contaminants. At the same time, the rates of those mineral dissolution reactions are the primary mechanism that generates alkalinity that we need for the oceans to keep climate stable over million-year timescales. And so these were two connected areas that we worked on for a long time, really trying to understand the rates of processes and how some of the products, whether they're contaminants or something like alkalinity coming from rocks, is transported through groundwater to rivers to oceans. And relatedly, around 2010, people started to get interested in this idea of mineral carbonation. So this is reacting things like carbon dioxide, which in some cases, many cases, you could think of as a contaminant, reacting it directly with rocks to form carbonate minerals. And so we worked on that for a couple of years. And I think at the time, it's fair to say that a lot of people thought this was sort of a fringe technology, that we wouldn't really be trying to carbonate rocks at scale. But then things started to really change in 2018, and I'll tell you a little bit more about what happened. And I started having people reaching out to me to ask for technical evaluations of a lot of different projects involving rocks. And this was carbonating rocks, dissolving rocks, and got really interested in the problem of carbon dioxide removal and how to bring some of the science and technology that we've worked on for so many years from kind of a basic science perspective into play in terms of thinking about how we deploy some of these different carbon removal technologies. And so we've sort of developed a portfolio. One area that I won't talk so much about today is how do we harmonize the science and the physical laws and behaviors of these technologies with the markets that we need to deploy them at scale. And then we've also started working on biochar, which I'll say a little bit about just as a comparison to enhanced weathering. And then the bulk of the talk will focus on enhanced weathering. And so this is kind of fun for me because a lot of this modeling work I've done myself, and normally as a senior faculty member, we don't get to do a lot of hands-on research. So it's been really kind of fun to sort of get back into working with models and exploring different ways to use them. So that'll kind of be the bulk of it. But I did want to start off just with a little bit of a primer on carbon dioxide removal. And, I know that Google has been a really important voice in thinking about how we start to scale CDR. And so many of you are probably very familiar with it, but just in case, I'll sort of start from the beginning. And as I mentioned, 2018 was sort of this pivotal period. And what happened in 2018 is that after we signed the Paris Agreement in 2016, which was such an important time and demonstration that we do think that collectively we can address climate change and try to keep temperatures to 1.5 to 2 degrees C as per the Paris Agreement, the question was, how do we actually do that? And so the IPCC convened a group of integrated assessment modelers in 2018 and looked at, how do we keep temperatures below 1.5 degrees C? And so on the left here is just kind of a summary plot showing global emissions trajectories for the different integrated assessment models that achieved that 1.5 degree target. And so the top up here, the low energy demand scenario, you can kind of see that one curbing pretty sharply and then crossing this line of net zero. And then you can see the more extreme case of the fossil fuel development case. And what you notice about all of them is that emissions fall pretty steeply, but then they go into this negative terrain. And so what the map on the right is showing you is that the longer we delay reducing emissions, the more we're going to need carbon dioxide removal. And basically every single model in the IPCC scenario to achieve this temperature goal had carbon dioxide removal in some fashion. The difference depends on what we view as what are the hard to abate emissions. So if you sort of look over here at the right, you can see there probably will always be lingering CO2 emissions that need to be offset by carbon removal, but we also need carbon removal to steepen the decline in overall emissions. And so just to kind of give you a flavor for the magnitude that we're talking about here, it's really enormous. So we're talking about roughly 100 to 300 gigatons of removal by 2100. Most people think we need more than that. The target is sort of 10 gigatons per year. And that's an enormous amount. That is probably bigger than any industry that exists today, including oil and gas. So we're talking about moving around a lot of carbon and somehow storing it securely. The thing that I think is important, and those numbers are big and they're daunting, but it's also true that every ton matters. So every ton that we don't emit or every ton we remove today matters for the overall warming trajectory. And that's because the radiative forcing is cumulative. And this is another figure from the original IPCC report, just getting at that point of you know, the necessity to take action soon, and that every ton does matter. Of course, I'd be remiss if I said that every ton we remove is equal. And this is a figure from a paper, a recent paper, looking at how important is it that these removals are durable. And what they're showing here is the additional warming relative to a permanent CDR. So you can see the blue line, which would be permanent carbon removal. And then as you step up to something with 1,000-year storage duration, as that CO2 is re-released, it contributes to additional warming. And then you can go up here to sort of 100-year storage and then direct CO2 release. And so the point here is that one of the things that's really challenging about CDR, but also really important, is that we really need to think about emissions as a permanent liability against the atmosphere. And so that has to be matched with something equally permanent. And if not, we have this risk of undermining climate integrity. And so this is where this question of durability comes into the CDR marketplace. And it's a really challenging science problem that a lot of people are working on. Some groups have come up with some helpful framings. So Microsoft and Carbon Direct have a nice report that kind of goes through and discusses this for each of the major pathways. We sort of took this and bended into the diagram on the right, where we're showing you know, a lot more of the biomass related storage or CDR pathways down at the bottom as being relatively short toward storage times, lower durability, moving up to biochar, which I'll say a little bit about, and then enhanced weathering, which we'll talk about. And then of course these, what we consider to be largely more permanent, which is mineralized CO2, things that are permanently stored in the subsurface. Of course, we're a long way from, you know, both the ambition of 10 gigatons per year and the realities of how fast we can deploy some of these technologies, particularly the permanent ones. As you would kind of expect, these high durability technologies like mineralized CO2, as I mentioned at the beginning, have pretty high capital expenditures and long time scales to development. And so what I'm showing here is a nice comparison that CDR.FYI put together of what's actually being delivered right now. So these are carbon credits that have been purchased versus what we're anticipating. These are pre-purchases, offtake agreements, things that are off in the future and have not yet been delivered. And so you can see pretty quickly, if you look at the left, biochar is really the technology that's delivering today, and it's been holding at about 90% of the durable deliveries. And of course, biochar is just biomass that's been burned in the absence of oxygen at high temperatures. And so it has this stability, and it also can be deployed on farms and in a lot of different places. So it has this nice kind of built-in scaling feature that integrates with agriculture. And you can see some of these other pathways, enhanced weathering, just starting to have deliveries of enhanced weathering, and a few other things, mineralization, BECCS, and direct air capture. And then, of course, if you look out to what's actually being pre-purchased, there's a lot of excitement about some of these nominally more permanent strategies, with BECCS being a big part of the portfolio, direct air capture as well. So I think, there's a lot of different ways to read this plot, but I think one of them is that, in the short run, we're going to have these shorter duration, these less durable removals. They have to be at play. We have to be thinking about forests and biomass and some of these things we know can work today, given everything I just told you about the realities of the need to remove CO2 and reduce emissions as soon as possible. So you might ask, okay, well, why are we so worried about durability? Why can't we just replace them? And I think it's important to distinguish between durability. It's really an asset of the class. It depends on the physics, the risk, a bunch of different things that are inherent to a particular asset class, whether it's a forest or biochar on a farm. And you can think of permanence as more of a system commitment. And this won't be a surprise to anyone. We're really bad at thinking about long-term commitments. And so, in theory, we can say that contractual permanence is possible. But, where we are right now, the markets just aren't set up to accommodate it yet, I hope. And, the other issue is more of a systemic one, which is that, I don't know if anyone's a skier, but if you're used to seeing like pinwheels on a ski slope where they get bigger and bigger and bigger, replacing an asset like a forest that's been degraded or impaired is really challenging over time. And the more that we scale CDR, the harder it's going to be to have this replacement mechanism to ensure permanence. And so a couple of different reasons why it's challenging and why there, I think, is a lot of focus on this question of durability. And, this is sort of a hodgepodge slide here, but, the challenge in markets is that the way they're set up now, we're really not enforcing permanence. We have things like retirements, and so this sort of ends accountability. We tend to equate non-durable removals with durable ones in terms of how we're using them to offset emissions. And a lot of times where we're really mixing what should be the physical underpinnings and physical accounting and quantification with constructs that largely come out of the Kyoto Protocol. So there's a lot of challenges in terms of thinking about how to handle permanence in the context of the need to reduce emissions and trend towards a net zero emissions landscape, and also just a lot of different ways people are thinking about them. And I'm not going to talk about the trade-offs, but you can think about, insurance programs, holding these buffer pools, different ideas for how we can blend different types of carbon assets, 10-year accounting, and then this idea of limited term crediting or effectively leasing the carbon for a short time scale so you can actually re-verify it and ensure that carbon is actually durably stored. But, I think what is the real challenge in terms of reforming the markets and getting to what we believe as like credible markets and creditable CDR is what I call the CDR time curve. And this is what we're really focused on for some of these different technologies and thinking about how do you develop these, what's the role of models and helping us to predict these curves. And this is an example from a paper we just wrote on biochar. And what's happening with biochar is that you take the tops from the field, convert them into biochar in a pyrolysis reactor. The crediting happens at that point. So based on the hydrogen to carbon ratio of the bulk biochar, you decide that this biochar has a certain permanence level. And this is usually kind of defined for a 100-year scheme. And so effectively what we're doing is we're taking short-term kinetic experiments that are usually done in the lab in beakers where we've reacted biochar with oxygen and water and CO2. And extrapolating that out to these 100 to 1,000-year time spans. And so, what we were able to tell from looking at all of the current standards in the marketplace was that probably we're being conservative, and that's a really good thing. But it also means that we're leaving this kind of dark matter of carbon on the table in terms of not crediting what's actually being removed. And again, when we start to think about this 10 gigaton scale, this efficiency and being able to credit and understand what's stored and what isn't stored is incredibly important. And so this is, the blue is sort of showing what we mean by a CDR time curve. And so of course, biochar is decomposing over time, so we're losing some fraction of it, but you do have this big, massive uncredited mass. And of course, the logical thing to do is to go back and remeasure the biochar at 100 years and make sure that what you thought should be there is still there, but that is both expensive and one of the things that's hard to do in the way that we're currently setting up the markets. So this is what we're, yep.
I mean, this observation applies to biochar, but of course, forest as well, because for them, the curve will be shifted farther to the left, but it's it seems like the same idea, just like more like decades as opposed to centuries. Is that fair?
Absolutely, yeah, no, I mean, I think these CDR time curves are super important for all of the different pathways. Forests, you can think about them as accruing carbon and then reaching a steady state. With forests, I think you have a lot more risk of an impairment, whether it's drought, whether it's a fire, whether it's insect. And so you could think of them as these like, you know, curves that might have a big dip in them, but really understanding the trajectory of these different carbon pathways and what an individual asset, what is a forest in California like relative to a forest in Brazil? Those are the kinds of questions where I think we really need to get granular. And so I'll talk about one set of models for enhanced weathering, but I think we need this capacity across this whole space. Does that help? Okay.
Yeah, and also you put confidence intervals in implicitly, that blue region. How does the probabilistic behavior affect the analysis?
Yeah, I mean, super important. You know, I think regulators and a lot of people are uncomfortable with uncertainty, and so they want that one single number. But I think, you know, from a governance perspective, deciding like, are we crediting at the bottom of that confidence interval? Is that the safest place? And, you know, I think it's a challenge because how much do we really even know uncertainty looking out over these 1,000-year time spans? It's probably like a question that, you know, statisticians who have a lot more perspective on how to think about uncertainty, but it's something we've been thinking a lot about in terms of how do you quantify the uncertainty. And as I said, it's very different if you're in a place with some known recurrence interval of fire versus other places, for example, for a forest. So I think a lot of work to be done there in terms of using the models in such a way that we can get these more probabilistic forecasts and have some comfort in that low level and high level uncertainty.
Got it. Thank you.
Yeah. Okay. Yeah, so this is biochar. You know, biochar has been around for a long time. You know, but still, I would argue we're lacking some of the data from controlled field trials and things we need to actually really understand what this CDR time and uncertainty over time curve looks like. Okay, so that's biochar. But what about rock? So the way that enhanced weathering works is that typically you take fine-grained crushed rock. Often this is left over from quarrying or mining activity, usually chlorine. It's usually what we call basalt, so it has a lot of calcium and magnesium in it, and we spread it on fields. You can spread it on forests, you can spread it on agricultural lands. As that rock dissolves, it produces alkalinity, and that alkalinity has to go through the groundwater into the rivers and make it to the ocean. And once it's in the ocean, it affects in subtle ways the partitioning of CO2. And so that's where you achieve a durable removal, is once that alkalinity makes it to the ocean. And so really the expectation we have around enhanced weathering is that the alkalinity we're generating in shallow soils is both quantifiable and more or less conservatively transferred to the ocean. So alkalinity tends to move more conservatively through the system compared to something like dissolved inorganic carbon, where you can have degassing of CO2 to the atmosphere. But of course, if you have carbonate precipitation in the river, then you're effectively impairing the alkalinity asset that you've created. So there's a lot of things about enhanced rock weathering that have resonated, and that's resulted in a lot of investment. So this is just kind of some headlines of major investments in enhanced rock weathering for a couple of different companies. Madi Carbon doing a lot of great work in India, just recently won the X Prize, and a lot of offtake and pre-purchases for a bunch of different companies. And so, of course, when a pathway starts to grow, it also begins to raise scrutiny. So a lot of people have been looking at the rates of mineral dissolution and wondering whether they're fast enough to achieve CDR and the timescales and at the rates we need. And of course, with all these companies, this is a new technology. So there have been a lot of experiments, and some experiments have gone well and other experiments haven't delivered. And so this has kind of raised a moment where we're not sure we have the measurements right. We're not sure that we have the scaling right. And so this has led to this question of sort of, does enhanced weathering actually work? And I'll just point to a nice little thought piece from the folks over at Carbon Plan on this question. And, you know, I think the answer is we're still learning. What I want to talk about today is, you know, how can models be a part of helping us learn and helping us to understand the role of enhanced weathering in this portfolio of climate solutions? And so what I can say is sort of absolutely enhanced weathering works. We know that chemical weathering, the breakdown of rocks on the continents, is the main mechanism that has controlled atmospheric CO2. The problem is that it's done it over a million-year timescales, and those are just too slow for us from a climate solution space. And so we absolutely know that weathering works. It is the primary mechanism for controlling atmospheric CO2 over long timescales, and a lot of groups have worked on this. We've done reconstructions of the carbon cycle over millions to tens of millions of years and found that amazingly chemical weathering adapts to keep pace with whatever is happening with the degassing and volcanic emissions. Those are also a lot lower. The amount of CO2 that volcanoes release is significantly lower than what humans are emitting. Humans are about 100 times volcanoes, just to give you a sense for the magnitude of emissions between natural and human driven. And so what we did here is we wanted to look at what are the rates that are actually coming from purely volcanic areas and try to just establish a baseline. And, it's arguable whether this is a high baseline or a low baseline, but it's a baseline that I think is important because these are areas such as the Philippines, Iceland, Hawaii, where you have entirely basalt weathering. And so the amount of surface area and fresh rock that water is seeing as it goes from rainfall through the soil, through the groundwater to the rivers is pretty enormous compared to the relatively small amount of rock we're putting on fields. And so I still think these are kind of relevant, even though there certainly are some differences. And just to give you a sense for the scale, global basalt weathering today is removing about 0.04 to 0.06 gigatons of CO2 per year. Remember that sort of, 10 gigaton number. Global silicate weathering, so this is all the rivers in the world, contribute 0.24 gigatons of CO2 removal via the oceans. And, we're still figuring out what we think enhanced weathering can do. There's everything from sort of 0.5 gigatons per year up to 5 gigatons of CO2 per year. And I've seen integrated assessment models that are relying on 10 gigatons per year. So that's a really massive enrichment in alkalinity supplied by rivers. And you can sort of see that relative to this kind of global benchmark of 0.24 gigatons. And just to kind of give you a sense for how we arrive at these numbers, mostly what we see is, regardless of location and climate, we're seeing this kind of median of about 0.2 gigatons per hectare per year. And this is normalized by the land surface area, and I'll explain why in a minute. But how we compute these is by taking the measured concentration of bicarbonate in the rivers and the instantaneous discharge. And so you can see here, this is for a couple of individual rivers. At low runoff or low discharge, you have pretty high concentrations. And as you start to increase runoff, the kinetics of the minerals just can't keep pace. And so you have this dilution. And so this points to a couple of challenges. You have to be able to take these relatively noisy baselines from a natural river system and convert them into this flux measurement. And that involves some challenges in terms of being able to measure discharge and bicarbonate concentrations. We can, just as I switch slides here, go ahead and keep your eyes on the left. And so what I'm going to do in the next slide is replace this column of the sort of global basalts. And these are a compilation that spans a lot of different places around the world. It's a little bit challenging in that their discharge measurements were lacking in a lot of places. And so there's some question about the magnitude of these. But, I think generally you can see that the median across a lot of these different basaltic provinces is pretty similar. So keep your eyes on the left. I'm going to switch to comparing all of these natural rates to what is being reported for enhanced weathering. And so this is a mix of just everything that's been reported. So I didn't discriminate, but I did distinguish between field, model, and experiments. And the one blip in this slide is I couldn't figure out how to get Python to not show the original points for the violin plot. So everything's kind of double plotted, but you can see which points are from models versus experiments. And so, on one hand, you could look at this and say, wow, we're really enhancing the efficiency of weathering by applying rock. Or you could really start to wonder about, are we measuring this correctly? Are we really over exuberant in our expectations? And I think there's a little bit of both happening when we look across these broad rates. But this is pretty massive from, 0.2, which was our global median, all the way up to 20. So this is an enormous range of of rates being reported for ERW, and some of these probably just really aren't realistic. One of the challenges we know from trying to model rivers is that detecting these signals, CFT in the subsurface, is hard. So we'd love to think that we could monitor enhanced weathering by looking at watersheds and detecting the change in alkalinity. This figure is really kind of getting at, this is easy if you're looking at a batch reactor in the lab. It gets a little bit harder as you go out to profile scale. And once you start to get to hill slopes, you have a range of different flow paths. And so you have this mixing process that effectively can dilute the concentration time signal. And so when you get up to catchments, what you often see is this apparent reduced efficiency because of this mixing of different waters. So it's hard. Yep.
To what extent, like you're doing transport now, but to what extent does it matter? I guess you've shown that you can capture well in soil and then it gets washed out. To what extent is it actually being lost, or does it just like how it leaves, not whether it's persistent?
Yeah, that's a great question. That is almost entirely the focus of the rest of the talk, is that question. Yeah, I just wanted to explain why rivers are hard as a monitoring tool. And so because of that challenge with using groundwater and river water, there's been a shift towards what we call the near field conformance zone. And so this is really looking at the shallow soil, typically 30 to 60 centimeters. And so you can see there's sort of a control plane in here between what you export from the soil, which is that reaction zone where you've applied the feedstock, and then what you might see downstream in the groundwater and the river system. And so it is really about alkalinity export, but given the difficulties, especially when we're at small scale of measuring in river systems, there's emphasis right here on what we call the near field. And so typically what people are doing is measuring the solid phase depletion. And so you do this by assuming that there's some immobile tracer that's present both in the soil and in the feedstock. And so if that immobile tracer doesn't change over time, you can use that to compute how much feedstock was dissolved. Again, that's entirely based on solid phase, when what we actually care about and what matters for the ocean is really the alkalinity flux. And so keep in mind this idea of control planes. We're basically going to look at this one between the soil and groundwater. The other thing that the sort of current MRV measurement reporting and verification standards don't require is what I think of as closure. So it would be really nice to say that we measure the solid phase and we measure the aqueous phase and we actually get the same answer. And so right now that's not required. You can just measure the solid phase. So I'm going to just torture you all with a little bit of chemistry for a moment, but I think it's important to understand the differences in some of the ways that you conceptualize the reactions that are actually happening. And so this is the sort of canonical enhanced weathering reaction where you have, in this case, a calcium silicate reacting with CO2. It produces calcium, silica, and bicarbonate. This is technically correct. There's nothing wrong with this reaction, but you have to remember that it's actually just a statement of carbonate equilibria. It's not actually what's happening. What's actually happening is that protons are attacking the mineral. They're exchanging for calcium and breaking down the depolymerizing the silica to release calcium, silica, and water. So what you're actually doing in enhanced weathering is consuming protons, and that's the way I like to think about it. Why does this matter? It matters because there are a lot of sources of protons in soils. So there's soil respiration. This is the conversion of organic matter to CO2. There's secondary mineral precipitation. Secondary mineral precipitation is basically effectively running this reaction backwards. And so you release protons when you precipitate things like clays. Fertilizer inputs, you can have oxidation of the nitrogen sulfur species. And then this other thing, which is mineral surface exchange. And this turns out to be a really important one and isn't one we tend to think about a lot in our everyday life for good reason. So I think it's actually sort of misleading to write the reactions in terms of CO2. That's what we would like to expect, but it's actually really the alkalinity that matters. And so if we start to think about the proton balance, that really shifts your lens in terms of how you define enhanced weathering. And one of the reasons why I think thinking about protons is really important is this issue of soil pH. And so this is a map from soil grids of the shallow soil pH between 5 to 8 is the color scale. And so you can see a lot of the world's soils are really acidic. And this impacts the efficiency of fertilizer application. So if it's low pH, you don't take as much nitrogen, and it also impacts yields. And it's a pretty big lever in the global food supply, is just to shift soil pH. It also means that for enhanced weathering, low pH soils are actually really inefficient. You don't actually partition DIC into CO2 into the dissolved inorganic phase, which is what we're currently crediting on. Again, this reaction here in terms of CO2. And so this is just a nice figure from a paper a while ago looking at MRV, and what they're showing here is that effectively, as you go down in soil pH, depending on your soil PCO2 X stars, the inefficiency in the CDR uptake, in this case carbon uptake into the soil solution. And again, this is based on inorganic carbon, not on alkalinity. And the other thing they're assuming here is that soil pH remains static. But we know if you put rock on fields, we've been putting rock on fields for I think hundreds of years now, to actually fix soil acidity. And so this little marketing campaign over here on the left is from a company that works in the Midwest, talking about the importance of continuing to put what we call agricultural lime. So this is calcium carbonate that you put on soils to raise the pH up to agronomic levels. And it depends a lot on the crop, but 6.5 for something like corn is a typical pH level that people are trying to achieve. And some of our soils in the Midwest can have soils as low as pH 4 to 5, largely coming from high fertilizer inputs. And so we've been applying lime on soils for a long time to improve soil acidity, increase crop yields. It turns out we're also really bad at it. And so this is just a fascinating plot that I saw in a talk by Robert Miller from the collaborative testing program, where they took one soil sample and sent it to all of the soil testing labs that were willing to take it. I don't know, there's probably 30 soil testing labs, and had them predict how much lime to add, how much rock should be added to the soil to neutralize the pH. And you can see everything from close to 12,000 pounds per acre all the way down to less than 2,500. So this enormous range of predictions. And this is because we're just really bad at understanding what's going on in terms of controlling soil acidity. And so now we have enhanced weathering coming into the picture, this question of, can it displace agricultural lime? Can it provide these co-benefits of increasing soil pH, positive impacts on crop yields? Is there a positive overall impact on soil health? But it's coming into this context where we actually have a lot of uncertainties just about how the current system is working. And so we wanted to think about this a little bit in these pH buffered soils, which is a large fraction of agricultural soils. What controls the alkalinity export? How efficient is the application of rock, whether it's lime or calcium silicate? And what are some of the trade-offs between an ag lime, the traditional calcium carbonate, and a calcium silicate? And the challenge is there's a lot of different controls. I've mentioned all of them. We'll look at a few of them, particularly soil pH buffering now. But the challenge is you really need a model. And my friend Jenny likes to call me an alkalinity maximalist, and that I think this is the most important metric, but it also requires a sophisticated model to try and track it. So we're going to sort of abstract a little bit on this MRV picture. And so I thought I would say a little bit about, what are these different models? What are these reactive transport models? And this is a figure I made from a review article a couple of years ago, just summarizing what these models contain. So the transport features, the geochemical features, and then also the sort of numerical and computational features. And, really, I think huge kudos to Department of Energy in the United States and some of the other agencies and other countries for recognizing really 30 years ago was probably when these models started to be developed, that understanding subsurface processes and having quantitative representations was going to be hugely important in the future. And so there's been enormous investment in national labs and by federal agencies and building the underlying capacities of these simulators. And it really started with nuclear waste management and groundwater contamination, but now really broad use in the geosciences for understanding the subsurface. And the nice thing is that, as we're sort of indicating here, is that there's a standardized process representation, and many of the 12 models that are shown here, summarized here, have been benchmarked against each other to understand how subtle differences in process representation manifest. And then we have more or less agreed upon underlying thermodynamic data. And so what we've been trying to do is take one of these underlying RTMs called CrunchFlow, which is a Department of Energy, Lawrence Berkeley National Lab simulator, combine a new representation of soil pH. So getting at this problem of we're actually not really very good at predicting how much alkalinity to put on a soil to raise the pH, and then a labeling system that we developed. So this is the tracking method that enables us to figure out which reactions are driving which response in the alkalinity profile. And then we combine that with distance-based generalized sensitivity analysis, which just helps us to establish some of the drivers in these nonlinear simulations and supports down the road a data assimilation process. We're just not to data assimilation yet. So the soil pH, as I mentioned, we really need to be able to track protons moving from the surfaces into solution. And this is really critical for separating out which protons are actually driving enhanced weathering. Right now, the standard is that it should only be carbonic acid weathering that counts as a credit, but you have this enormous reservoir of protons in the surface. And so how do we either separate those or just decide to focus on the net alkalinity? It turns out this is really challenging because the way that most soil data out there is designed is it's designed to be operational. It's for farmers to make decisions about how much fertilizer to put on their soils. It is not designed for Kate to run a reactive transport model. And so this has been a real challenge, and it's taken a long time to try to understand how to actually use this wealth of highly standardized soil data, and how do we get this into a mechanistic geochemical model that wants very particular things. So we've been working with the Kellogg Soil Survey and their database. And one of my favorite things is that they not only give you everything you want to know about a soil today, but they also publish all of their obsolete methods. And so there's really an incredible history of soils and methods going back to the early 1900s that we can harness. But we had to figure out how to do this translation, and this took me a long time to figure out. So what I'm showing here is, again, just a reminder of this global distribution of soil pH, where in wetter, warmer climates, we tend to see very low soil pHs. The bottom one is showing what's actually going on the surface. And so what happens with surfaces is that low pH protons bond to the surface, you form this neutral surface species. As pH increases, those protons the surface deprotonates and those protons go into solution. And that's actually what's neutralizing soil acidity. And that's why there's so much uncertainty on how much agricultural lime or rock to add to a soil. And so what we had to do was basically translate the KSL soil data into this bottom figure where we have this mechanistic representation of all the species on the surface. And so this is just showing that when we take the KSSL data, this is actually without any calibration. So this was just computation directly from the KSSL soil data into the model. And you can see we actually do a pretty good job of predicting the increase in effective exchange capacity. So this is both the desorption of protons as well as the sorption of calcium and magnesium onto the surface. So we're able to, we think, pretty accurately track the proton budget.
So question.
Yeah.
Soils are a mess in terms of like the dynamics, the amount of like roots in their bacteria and so on. So to what extent do we understand this dynamics, or to what extent do we need more data?
We always need more data, Greg.
Yeah. And my impression was just like the like a lot of the second order effects of bacterial interactions with soil for crop yield stuff are still poorly understood. But for enhanced weathering, do we have a decent handle on it?
No, I think we have a good first order understanding. I think as I'm about to show, if you're willing to kind of say, okay, well, let's assume we kind of have the basics right, and let's look over a broad parameter space and see what emerges as being important. I think we have the ability to do that. Certainly, like, the process representation isn't perfect. We don't have great plant root uptake in the model. So we're still missing some things on process representation. I also think we know generally how they behave. And so if we're really looking at trying to understand this broader scale question of how important is something like soil pH, I think we have the ability to do that. That makes sense?
Yeah, it helps a lot. And the other thing is you're pointing to difference between different soil depths and things like regenerative ag and those folks. For them, their treatment of soil depths is still very much emerging, like with tillage affects shallow soils versus deep soils. To what extent, is this a thing for enhanced rock weathering?
Yeah, I mean, that's a great question. I'll show you how the model actually ends up being discretized in a second. Traditionally, because the upper 30 centimeters, 25 centimeters is where the feedstock is deployed and where it's mixed, and it's also where we can measure. That's been the focus. If you're really thinking about alkalinity export, you need to look deeper, and you can kind of see here, this is the deep soil from about 120 to 300 centimeters. There's still a lot of exchange capacity here, which means it's playing a role in attenuating the alkalinity inputs that you do in the shallow zone. And so it's challenging. It's hard to access the deep subsurface and the deep soil. But for alkalinity, it's important if you're just looking at soil organic carbon, it may be less important to look as deeply.
Thank you.
Yeah. No, and that's why I think each one of these, these pathways has their own kind of modeling needs and data needs, and they're all very different depending on where you need to track the fluxes. So we've also added a labeling system, and I know I'm kind of running short on time here. This is super simple. The only thing that was hard about it is that numerically these tracers cause some problems in the Jacobian in the model, and so we had to think about how to set them up so that we could actually solve the system of equations. But otherwise, basically what we do is add a label to each mineral reaction, and that enables us to figure out who provided the alkalinity, who took up the alkalinity from a reaction standpoint. And so the model we'll look at here is built off of this acidic soil in Illinois. And what we've done is break the model into 3 zones. So we have a shallow zone where the feedstock is mixed, the sort of deeper BT horizon, and that's BT horizon is just a clay-rich horizon, and then a deeper soil horizon. And we're adding precipitation at the top. We'll look at what would happen if you only measured at 25 centimeters, which is kind of that typical MRV zone today. And then we'll look at what happens at 300 centimeters and how different those two are as you traverse this deeper section. And so we're treating it as unsaturated flow. We have soil respiration included, and so we pump CO2 into the soil environment to generate what would happen from root and microbial respiration. Typically, those are about 50-50, so we just try to match that same flux of CO2. And then what we'll do is look at some distance-based global sensitivity analysis. And what this enables us to do is say, okay, well, we think we have one soil that's reasonable approximation, but what we really want to know is how important is it to have this strong surface buffering. And so we can vary the silicate and carbonate amendment. We can vary the rate constants for the underlying minerals. We can change the hydrologic parameters. So how saturated is the soil? What's the Darcy flux? The surface proton reservoir here is shown by these site concentrations at different depths, and then we vary the soil respiration rate to look at that forcing. So we're kind of covering a broad range that's set by what we think is expected from agricultural soils, but not trying to really pin down one set. And so I'll show you, this is what it looks like across this pretty broad range of parameters for a calcium silicate amendment. And again, we're sort of simplifying basalt amendment and representing it as a calcium silicate. Normally there would be aluminum in the mineral. This is actually a mineral called larnite, which is starting to be developed to put on soil. So we wanted to look at it from that perspective. I'm going to keep it simple and not show you all of the different minerals and amendments. So we'll just look at the calcium silicate versus the carbonate amendment. And so the top is what would happen if you measured at 25 centimeters. The gray is the potential alkalinity. So that's the amount that was put in based on the amount of tracer that was released. And so you can see that in some cases, the exported alkalinity comes up and achieves, relative parity with what we put in from the feedstock perspective. The dashed line here is at 10 years. And so today we're crediting at 1 year. This is just a 10-year horizon to say, okay, what if we look at it at a 10-year window? The bottom is showing the 30 centimeters, and you see this delayed arrival of the alkalinity at this deeper depth, which has to do with the surfaces exchanging protons above. And So for Larnite, we see a really nice pH response. The ones shown in red are just indicating that it's a non-agronomic response. It would be too high for a crop system. It would actually probably harm the plants. But most of them deliver an agronomic response, and you can see that that's attenuated at depth, much less pH response at depth because of the surface buffering in the system. And then, surprisingly, or maybe not surprisingly, calcium carbonate behaves exactly the same. So the amendment rates were scaled by the theoretical alkalinity loadings, and so these should look the same. Of course, when you add calcium carbonate, you're also adding carbonate, so we don't see the big pH shift in calcite. That's the one difference, is that you're sort of protected from these really alarming soil pH shifts from the carbonate that you're introducing. But otherwise, the almost identical responses between these two feedstocks. We can also use the sensitivity analysis to tell us what matters if we're measuring where. So really all we're detecting, if we look at the 25 centimeter control plane, is the volume of mineral added. And that comes up as the most sensitive parameters, with the site concentrations, the surface proton reservoirs being sort of barely sensitive, and then a bunch of other things like hydrology and underlying mineral dissolution rates being far less sensitive. That shifts as we look deeper. We actually see that it's the mineral application rate plus the surface proton reservoir, these site concentrations, that are generating the most variability in the observed alkalinity export. And so telling us that, things shift as we start to look deeper, as you would expect.
So question,
Yep.
This is for like a single application. It looks like so it's like there's a spike and then
Yes.
it comes down, and at the bottom it just kind of sits there. What happens if you keep applying it?
Yeah, so the typical reapplication rate for Lyme is about 4 years. We didn't do that here. We wanted to just track a single pulse. But yeah, absolutely. If you're in some ways never going to let a soil, you wouldn't want to let a soil acidify, you'd be reapplying. This was a question. In that case, you would never recover the alkalinity. The reason why you recover your alkalinity here is that as the soil reacidifies, you basically recover the alkalinity that you lost from the pH amendment. So one of the questions was like, do you actually recover? How reversible is the alkalinity loss? And so, we're showing here it's pretty reversible. It would be much less reversible if you kept putting rock on the field every 4 years, which is kind of the typical amendment rate.
Yeah, that makes sense. Thank you.
Yeah, that was a good question. The current proxies, as I mentioned, solid phase is one of the main methods. People are also looking at selective leaching. This is like usually a strong acid leach, and then, measuring the actual alkalinity flux. And so this is a recent set of experiments that compared these 3 different measurement proxies, and you can see they're pretty vastly different. So it's really challenging to know what to measure. Even cation leaching, surprisingly, was a pretty poor indicator of alkalinity, if you believe that the alkalinity export is the metric we should be focused on. Of course, alkalinity probably doesn't tell you how much weathering you had, and so it's just a balance between what do you want to actually assume as the basis for deciding whether it's an EW, CDR removal. So we wanted to look at proxies, and so here, this is basically pretending as if we could measure calcium and use the model to look at it. And so what I'm showing is calcite on the top and the silicate on the bottom, and this is calcium relative to the alkalinity export and DIC export relative to alkalinity export. And so you can see that in neither cases, neither proxy, calcium or dissolved inorganic carbon, is actually a very good indicator of the alkalinity, and that just comes from this decoupling both in the surfaces. And then, as you can see, particularly for Larnite, it depends a lot on the soil PCO2. And so because you're not introducing carbonate, you have this decoupling of the DIC from the alkalinity, which is purely driven by the respiration flux in the soil. And so we can kind of look at that in terms of, how much are we overestimating and underestimating? And it looks like it could go both directions. So in some cases, calcium, for example, could be conservative in terms of estimating alkalinity from calcium. And in other cases, it could be a pretty substantial overestimation. So this is a challenge for the proxies, and I think helps to explain why, we see results like this, where really different answers depending on what you look at. And so kind of the final thing is that, this ability to bring in mineral tracers in the simulation is really helpful in that we can actually see how the partition shifts over time. So if you're just looking at this sort of 4-year simulation time, this would be, Greg, to your question, when you would probably reapply. You have really, really high loss fractions, and that's just this initial surface neutralization that you're seeing. And then the actual loss fraction goes down over time as the system reacidifies. But what happens is that you actually perturb the underlying native soil minerals, and so you get a bunch more clay precipitation by introducing the calcium, aluminum, and silica. And so the mineral loss, the fraction of alkalinity that's due to mineral precipitation, is increasing over time. And so this starts to give us an understanding of the time scales. And then, finally, the last piece that is really important is that ag lime is different from Laranite, even though it looked the same through a lot of these different simulations, and that you actually do take a short-term hit. And what's shown here is the cumulative reduction in CO2. So positive means that we're reducing the flux back to the atmosphere from soil respiration, and negative means that we're actually increasing that. And so over time, this is at 10 years on the left, and then the histogram is showing over 150 years. Over time, we still see net removal, but if you were really looking at ag lime on short time scales, you're actually, could be increasing the amount of CO2 going back into the atmosphere from adding calcium carbonate because of that carbonate component. So that is a really key difference, even though the alkalinity and DIC export is the same for both minerals. So just kind of wrapping up, this was really looking at this question of how much do we need to worry about soil pH and soil buffering, and I think the answer is we should really worry about it. It's potentially a big impairment of alkalinity depending on how the deployment is set up, and it's really challenging to bring in the data in terms of finding data on soils that can populate the models. Kind of zooming out for a second, today we're looking at MRV costs of $300 to $1,000 per ton of CO2 verified. That's pretty enormous, given CO2 prices in the market for something like biochar, $200 a ton. So we're spending a lot on MRV, which is driving up the cost. Can we use targeted modeling to help hone in on what are MRV strategies that reduce costs, but also make sure that we're delivering meaningful verification? The kind of build on this question of refining MRV and using models to help us do that is probably shallow soils are a misleading quantification target. We're going to have to think about deeper measurements if we really want to capture the true alkalinity export. And some of these traditional stoichiometric proxies break down. And finally, there's, as Greg nicely asked, this was a very simplified scenario of a one-time deployment. But I think, what I showed from the natural basalts as well as from the models is that the geochemistry really operates on a different time scale than CDR crediting. This 1-year crediting really maximizes apparent losses. And if you think about it from a loss perspective, you're actually better off reserving your MRV and waiting until you have a more clear signal. So, I don't think I've answered the question. It's still a big question, is how do we evaluate EW CDR assets? Right now we're using these local CO2-based approximations, which is, we measure whatever changed and assume a CO2 per cation ratio. I just showed you that doesn't actually work very well for calcium and DIC. Versus this more complicated scenario of measuring alkalinity export to oceans. And we can measure it from the deep soil, but we still have to figure out what happens as it goes through groundwater and rivers. And so those are two very different end members, both with a lot of trade-offs. In some ways, what we're doing now is sort of a double standard, and that we're crediting CO2 removal immediately based on short-term changes when we know that delivery doesn't actually happen for thousands of years until that alkalinity hits the ocean. On the flip side, an alkalinity export-based approach would be very conservative. We'd only really be crediting CO2 removal when it reaches the true sink. So not a clear question at this point, but I think a lot to think about. And I know I'm approaching time here, but I think more generally, and this question came up, is sort of what is the future of models in MRV? I hear from a lot of people that models aren't ready for MRV, and from my perspective, I think the measurements aren't ready for MRV either, and so I think there's this need to really have models in the loop early on, and to really start to use them as part of the MRV process today, instead of relying entirely on empirical measurements. And in the ocean alkalinity, they've done a nice job of really thinking about we should be doing MRV with models and building that platform and some of these other pathways. So carbon, biochar, enhanced rock weathering. We've been putting off investing in models, and I think that's a challenge moving forward. And there's other questions in here in terms of like who governs models in this space. Anyways, we're talking about money trading hands, and how does this get governed? How do we unlock data? What's the role of open source versus proprietary software? So a lot of questions to think about in this space. So I'll wrap up there and go ahead and take questions. Just want to acknowledge some funding from the Sustainability Accelerator and our collaboration with the Sustainable Finance Initiative, as well as NSF for long-term funding. So thank you.
Yeah, fantastic. Thank you very much. So one question, like this MRV question, is rather significant. Let me just poke at the long-term behavior of the enhanced rock weathering is going to be ocean-based, right? Like you flush it down to the oceans, but then no effect that we can have a measurable impact in the ocean. At least, like, it seems like rather difficult to imagine us actually saying the ocean is this much more alkaline because of these rocks. What can bridge the evidence gap at that level?
Yeah, that's such an interesting question. It would be fun to have someone from Seaworthy come talk if you haven't had Seaworthy on. Have you?
No, I'm not. That's
No. Yeah, they've been really focusing on these models of the ocean system, and so I think that's where the types of models that they're developing, where you could, so one of the things I'm really worried about is that a lot of rivers are already really close to carbonate saturation, and we really don't know how much we can increase the alkalinity of some river systems. Some river systems, yes, some river systems we might not be able to without driving a lot of carbonate precipitation. And so, I think there's an interesting experiment to be done to kind of take what we know about rivers and take their more advanced ocean alkalinity and really ask, like, what's the capacity, even if we could boost rivers by this much, to get this to the ocean, and how much of a difference would it make? And that may be another way to kind of hone into this capacity question. But yeah, no, I think it's a challenging problem. Certainly, you don't need to change alkalinity by that much to partition a lot of CO2. The ocean, I mean, that flux is, I don't know what that net exchange flux is, like 90 gigatons per year. It's quite enormous, and so subtle shifts in alkalinity have the potential for relatively impactful shifts in CO2,
Right.
Which is why there's a lot of interest in ocean alkalinity.
Okay.
But it all needs all of this needs so much more work. We're used to thinking about these slow long-term systems, and when you start perturbing them in these ways, like we're not there yet on having the models fully ready.
That makes sense. And then if you were to shift, so MRV, when you're crediting, I mean, what else are they going to do? But
right.
At least. But if you shift perspective, I think you were pointing to, well, if the effects you want to see are deep soil, maybe in 10 years, or effects down the river in 50, 100 years. If you were to shift MRV to what, statement about what measurements will be 50 years from now, does that simplify the problem, or does it just move it to a different, difficult measuring location?
Yeah, it's like there's two parts to that, because I think one of the challenges is when you're not at scale, the signals are very small, and so the way that you would want to detect something at scale is very different than what we can detect now, and I think that poses its own challenge. I do think that we would potentially make our lives a little bit easier if we shifted from this one-year crediting scheme to thinking about, we're deploying something now that we know will pay off in 10 years. And so you might be able to, to go in 5 years and do the measurements in a very selective way and say, okay, we have a signal, let's go ahead and do the MRV and establish the credit. Or we may decide that we have to shift entirely and really view this as something that isn't a, hate to say this, but isn't an asset per se, and that it can be used to offset CO2 emissions, but it's a good thing to do because it benefits soil health and crop health, and we know it contributes positively to ocean alkalinity. That would be very different from the way that things are set up now. But I think is one possible outcome. I mean, we certainly know that the rocks deliver benefits. It's just, does the time scale mesh with what we want to achieve with carbon markets and assets.
Got it. And then just conscious of time, just one last question. The biochar keeps coming up during your talk, and I just wondering how different or similar is that problem to the rock problem?
Yeah, I mean, it's similar in terms of dealing with these sort of questions of how do the complexities of a real soil environment impact biochar, and what we don't have for biochar are good ways to actually measure it in the field, and that's largely because the crediting happens when the biochar is spread on the field. It doesn't happen after it's sat in the soil for a long time. So in some ways, it's an even more challenging problem in that we don't have a great tuition for how biochar responds to being in a soil for 5 years. Does what we see in the lab actually scale to biochar behavior in the soil? So we just started some field trials, just trying to figure out, can we actually go back into a soil and measure biochar reliably over 1 year time scales? And so I think there's some work to be done to really convince ourselves that those curves that we're projecting out into the future are correct. So a lot of exciting work happening on biochar. It has its own similar but related problems. And I think with biochar too, similar to I showed some of the high pH simulations we were getting, doesn't always benefit crops. And so you also want to know, what types of biochar work best for what crops and on what soils. And so from a deployment perspective, there's, I think, a need for modeling strategies there too. We've just been more focused on some of the immediate questions around how do you measure it, and
Right.
and hoping we'll get some longer term experiments going.
Yeah. Well, yeah, thank you very much. This was fascinating.
How do I stop sharing here, Greg?
Actually, one more question from the call. Yeah,
Okay.
how transferable are the soil models from one soil to another? And how much local data do you need to adapt?
Yeah, it's a great question. One of the challenges is that we're pretty weak on actual soil data in terms of understanding the soil mineralogy. And so this is why we're kind of using sensitivity analyses to enable us to cover a pretty broad spectrum. So you do for sure really want to think about the local soil environment. I'm not so sure. I mean, I don't know. I may regret saying this. I have a feeling that things like the surface buffering that I talked about and the cation exchange capacity in some ways are probably going to be more important. But as I showed, there's this hint that the feedstock actually shifts the reactions in the underlying native soils, which would be really hard to test. And so, I have a student right now who's working on doing some simulations looking at soils in Brazil. And so, you might be able to be more granular on this. But certainly other things like the soil respiration rate, the amount of organic carbon, those things all play a role. The clay, whether it's clays versus some other surface that you're attracting. So people are working, there's a lot of work right now kind of going into these data layers for enhanced weathering to predict soils. And I think the challenge is making sure that those are model ready, and as I showed, a lot of times the soil data just doesn't work for models. And so I think there's also a connection there between how do we compile and organize the data versus how do we make sure it's model ready.
Right. So actually, maybe just expanding upon this, to what extent is this a rush? What I mean is, if I have a property, I want to apply the rocks to, do I have to measure this now, or can, if I had the luxury of waiting 10 years to actually do the measurements and to develop the science, actually spend the time, is that a viable path towards getting good estimates?
Greg, I would love it if you had a property and wanted to spread some rock and wait 10 years.
Yeah.
Let's do it. Yeah, no, I mean, so the typical way it works now is that you go out and you measure what we call the baseline of the soil. And so you would go out and you would characterize at some spatial configuration. It's a couple $100 a sample to do the baseline characterization. So that's what I'm talking about expense. But yeah, you would have your baseline sampling, you would deploy the feedstock, you might have a business as usual kind of control plot where you didn't apply the feedstock, and you'd be monitoring both of those over time. And so, yeah, traditionally you'd be looking for a signal that you could turn into a verified carbon removal in a year. But yeah, absolutely. I mean, if you had, you could also go out and do point sampling and say, no, we've only dissolved 10% of the rock. Let's wait another year. And then I'll go back and do my really robust sampling for verification. So I sort of like that staggered approach of let's measure a little bit effectively and then wait until we have a clear signal.
Right. You have to change the MRV policies to make it work.
Yeah, and also just the financial structure right now. I mean, that I think all of these companies would say they couldn't survive if they had to wait 10 years to sell a carbon credit. And that's where maybe there is other interesting revenue from ag line displacement and crop benefits in terms of, the other thing about silicates is some crops really need a lot of silicon. So boosting the calcium and silica as a fertilizer for some crops can be beneficial too. So there may be other markets that you could kind of do think about a dual purpose scenario.
Right. Okay,
Yeah.
cool. Yeah, that makes a lot of sense. Thank you very much.
Yeah.